everyone, and thank you for joining us for the fourth webinar in NAIADES project webinar series. And today's webinar is called Event Detection in the Water Sector. And we have an exciting lineup of both NAIADES presenters and external speakers from other projects. So just an introduction for the webinar. This session will be entirely recorded and published on the NAIADES channels. Please, everyone, feel free to post your questions for the speakers in the chat, and there will be time in the end to have a panel discussions where I can get the questions from the chat, and if we have enough time, the presenters can answer all the questions. And you're very welcome to share your thoughts about the workshop on Twitter via NAIADES project and linking NAIADES webinars hashtag. I am your moderator for today. My name is Tuuli Lõhmus, and I work for GuardTime, which is a project partner in NAIADES, and I'm a project manager there. And I'm based in Estonia. Today's agenda is to have two sessions for a 3-hour webinar, and session 1 includes 3 talks from NAIADES project, and session 2 has 4 presentations from Digital Water 2020 projects. And in the end, there will be, we'll see, about half an hour discussion and wrap up before we end at 1 o'clock. So without further ado, I will give presenter rights to Mr. Thanasis Anagnostis from CERTH, who is an associate researcher there and a PhD fellow in the University of Thessaly. And he will further introduce his topic and his research area himself.
Hi, good morning. Hi, so thank you, Tuuli, for the introduction. My name is Thanasis Anagnostis. I'm working at the Center for Research and Technology in Greece for the past 8 years. And my topic is data science and machine learning algorithms. And today I will talk to you about data-driven weather forecasting. So we all know what weather forecasting is. It is the application of science and technology to predict conditions of the atmosphere for a given location at a time. So science and technology is not very strict because we know that this has been done in humanity for millennia. We always wanted to predict the weather. We always wanted to know what the weather will be like in the future, because weather is highly effective on our behavior, on our operations, on everything. So when we speak about weather forecasting, we normally mention numerical weather forecasting, which is the conventional way of making predictions, weather predictions, which is by solving some very complicated equations of fluid dynamics and thermodynamics, because we consider the atmosphere as a fluid. It's a very big, a very chaotic system, and anyone who has tried to study a bit this subject would understand that it's one of the most complicated systems that physics have to deal with. Consequently, it's computationally expensive. And of course, when we discuss about weather forecasting, we discuss about some specific spatial granularity. We cannot know everything about all the places in the world. So when we discuss about this, we mean that the higher the detail of the forecast, the more expensive computationally and financially it can get. However, we don't need the same forecast for everything. The forecasting needs are not the same. So discussing about numerical weather forecasting, which is the conventional one. There are some pros. Of course, it's very accurate. We have extremely accurate predictions. It's physics-based, so it's explainable. It considers atmospheric phenomena, which is taking into consideration the whole atmosphere as a total. We get some big picture insights. We understand what's going on in our country, in the next country, in the next country, and maybe the next continent. And the results that we get back is has a very wide range of variables included. However, there are some cons in this. It's conditionally accurate. So when we discuss about some areas that suffer from microclimatic variations, it can be consistently inaccurate. Because the computations are very complicated, the microscale phenomena are parameterized, or we can just say directly ignored. It's very time consuming to run these algorithms. It takes a long time, and it's resource intensive because it needs computing clusters. So as you can understand, it's very costly in general. So how do we tackle the cons? There is an alternative. The alternative is data-driven weather forecasting. It employs historical data and AI algorithms to produce specific predictions. And AI approaches, they can solve only very specific problems based on the collected data that we have. So thankfully, we live in the age of data, and we can gather a lot of data from a huge amount of sensors and satellites and whatever we can imagine. We also live at an age that the hardware costs keep going down, with the exception of coronavirus, which has driven prices up, but it's only temporary, I hope. And we live at a point where the mathematics that drive the artificial intelligence are very powerful. Okay, so what is the reason why we need data-driven weather forecasts? There are some operational reasons. We can use it for city planning, which is directly related to the NAIADES. It's directly related to the NAIADES project. Also facility management, agriculture, aviation, construction, mining, event management, insurance, transportation, and many more that you can imagine. And some technical aspects why we need to use the data-driven weather forecasting. Data-driven weather forecasting deals with microclimatic effects. It can increase spatial granularity. It can reduce computational cost. It has the benefit that it continuously improves through time because of the amount of collected data. It's very easy to add and remove parameters and still keep running our models. And it can utilize heterogeneous streams of data. So in a very short terminology, we can say that data-driven weather forecasting, it can be used for hyperlocal weather predictions. Okay, one example for what hyperlocal weather predictions are. In the Formula One, they employ some very highly sophisticated data-driven weather prediction to predict the differences in the forecast between each corner. So there might be a circuit that in one corner we have sunny conditions with very high or low humidity, which the temperature will rise or fall, or the rain will come within the next 5 minutes. This is a state-of-the-art approach, and it can predict differences of very high granularity, both spatial and both timely. So what types of data and what types of analysis we do in the data-driven weather forecasting? We can get data from one-dimensional time series. We can get two-dimensional spatial data. We can utilize short-term, long-term, or even very long-term climate data. And from what sources can we get this data? Of course, weather stations, which is the most common. We can get them from sensors that are located on airplanes and drones. Recently, IoT cars like Teslas, they use and share temperature within their driving distances we get from cell towers. And there are some applications where they try to do weather forecasting from street cameras. So we can understand that there is huge potential for this method. So what is the relevance to the water sector? Here we see the city of Toronto, and we see the variability of temperature within the city. So we understand that there is a huge temperature variability in urban environments. The water demand and consumption is directly related to these weather conditions. Water utilities or municipalities, they can plan resources management based on the forecasts. They can plan localized operations, maintenance, and infrastructure repairs. They can prepare for extreme weather events like storms and heat waves and whatever. And they can implement precision irrigation. So, of course, we all know what microclimatic effects are. In a very small area, we have very different weather phenomena. One example, as we can see here, is the region of Athens. The region of Athens has 4 mountains and 17 hills within its area and 5 million population. So from what you will hear later on in this presentation, the management of such an area is very hard, and precise weather forecasting is needed. Another phenomenon that occurs in urban environments is the urban heat island, which can rise the temperature of cities just by having buildings in them, which is also a very microclimatic phenomenon as well, which affects the prediction. So what NAIADES weather forecasting aims to do? We want to collect data from multiple locations from urban environments. We train our AI forecasting models. We predict future conditions for each location, and then we create a localized forecasting service. So the desired outcome would be forecasting for very fine granularity in urban environments that would help the water managers and operators to plan ahead their operations. So let's talk a bit about our pilot cities. We have Alicante, we have Carus, and we have Braila. Alicante is a very hot, sunny, and drought area. Carus is rainy and cold, and Braila is cloudy and warm. Alicante is located in the south of Spain, and it has generally hot weather. Braila is in a plain. There are no significant mountains. It's also very warm, but in the winter it gets colder than Alicante. And Carus is surrounded by mountains. It's next to the Lake of Geneva, and it's a bit colder than the other areas, especially during the winter. So we use the same approach, right? It's not so simple because we have a very nice distribution in temperatures. However, the rainfall and the daily chance of precipitation are not the same for every city. As we can see, Alicante is relatively drought, and it rains only a few days per year. And some other variables that they are generally different. As you can see here, Alicante is very, very humid. However, we employ a very powerful neural network to tackle this problem for all the cities, the long short-term memory neural networks, LSTM, where it utilizes past values in order to make a forecast in one-dimensional data. So the technical implementation, how do we use this data and this architecture? We gather data, we store them into the database, we train the algorithms, then we produce predictions, and then we send them back to the NAIADES databases. And as a finalized approach, we utilize also data from the ECMWF, the European Center of Weather Forecasting. We utilize also different weather data from other sources like environmental weather stations that we are installing as the NAIADES project. And we are fine-tuning the models, and then we are producing forecasts. So for NAIADES weather forecasting, we make a look back of 360 hours, and we give a prediction of 72 hours ahead. So let's have a look on how these trained models perform. So for the training, we can see that the models are very accurate, and we see that we measure for all 3 pilot cities. We have temperature and we have humidity as well. We have atmospheric pressure and we have wind speed prediction. As you can see, wind speed is not so accurate as the rest. However, we have to understand that these algorithms, they are based on trends, and wind speed prediction is very hard to predict based on trend. However, it's still very successful. And some indicative results for Alicante. So the models have been training for 23 epochs, and we have very good error rate and very good coefficients of determination. In general, you can see visually that the models are very well trained. So how are these models perform when they are deployed in production? We have 5 use cases. We have Alicante, Braille, and Carus, but we also have a lab that we are producing forecasts for, and we have the environmental station, which is the station located in Carus. So we see these are the temperature predictions for each of these use cases. And you can see here that in the forecast, we include the error from the trained model. So we do not make exactly deterministic forecast, but we give a margin of error to be safer with the forecast. What we see is very interesting here, that we have some data gaps, which is an anticipated fault, which can occur by some malfunctions or error in the hardware. However, this is anticipated, and we have prepared and built our algorithms in such a way so that the forecast will be uninterrupted, even in such cases, by retrieving the last available data from further back. And all the forecasts are averaged for the sake of NAIADES in 6-hour intervals. So what are the cons for the data-driven weather forecasting? They are useful only for particular problems. We cannot, well, so far, we cannot model the whole atmospheric movements and what the numerical weather forecastings do. It's the black box phenomenon that is very well known in the AI world. It means that the models, they are very well in accuracy. However, they lack explainability. We cannot explain exactly what is going on within them. So we lack the explanation of physical phenomena. Training of the algorithms is computationally intensive. And AI at the moment has a very narrow view of the problem in most cases, however. But there are also some pros. There is data availability. We have a plethora of data which is available, and we can utilize them for building new models, for building new algorithms in order to exceed the state of the art. They do provide very high accuracy in the problems they can solve. They are very, very successful in it. Inference, not the training, is very fast and very computationally light in most cases, which means that when we train an algorithm, then a model, we can then deploy it in also in edge devices and even in cell phones, and it can be very, very light also in energy costs. There is huge parameterization and flexibility, and there is deployment versatility, which means we can deploy these algorithms in many cities if we train them good enough, as we're doing in NAIADES. So, are the hybrid models a solution, meaning that we can employ physical modeling and also AI? Who knows? The future will tell. So what's next for NAIADES and data-driven weather forecasting? Concerning time series data, we want to take into consideration phenomena that don't fall under certain trends, like it's the precipitation and snowfall and such things, or rare events like storms, blizzards, and heat waves that they are potentially dangerous for the water sector. We want to integrate spectral information, understand cloud type and movement, and understand when the precipitation is coming, and also again about rare events concerning the formation of typhoons. Concerning the deployment, we want to make them even more energy efficient and understand if it's better to deploy them in edge devices or cloud. Increase the parameterization for heterogeneous inputs, maybe deploy cameras and other inputs that are not deployed at the moment. And of course, listen to the end user's needs. That's all from me. Thank you very much.
Thank you, Thanasis, for this presentation. So our next presenter is also from NAIADES project, Mr. Nikolaos Angelopoulos, and he has been working in Konnektable since 2018 as an R&D consultant. And he has been project manager for several research projects and is working in big data analytics, and he will introduce himself further. So the floor is yours, Nikolaos.
Hello, everyone. Hello, I'm Nikolaos Angelopoulos. Nikolaos, if you want, I represent Konnektable in this webinar, and I will be presenting the work that has been done for the NAIADES project from our team, which is an interface, the front end of NAIADES, if you will. We will see also some of the, we will try to show you what the end user will ultimately see and use from the NAIADES platform. So I will begin. The HMI, as we call it, the human-machine interface, essentially the NAIADES front end, has been designed in order to facilitate the pilot needs. As Thanasis mentioned earlier, we have 3 different pilot cities, Braila, Carus, and Alicante. And so far, those are, we have not yet developed what is necessary for the water treatment plant and for the virtual lab. So this is what I'm going to be presenting you at the moment. So let's start and take a look at the interface for the use case of Braila, which is centered around the leakage prediction. Something very essential for the city of Braila and their water management processes. So what we do is that we try to build a dashboard which will bring valuable information for the end user in order to manage their processes in a more effective way. And further to that, our team is also designing a decision support system which will utilize all the data that are available to the user and combining it with the procedures that they have in place, suggesting some actions to take to mitigate any potential issues or to try and alert them in time for any such issues. I will move on and show you a little bit, let's say, component by component or module by module, what we see in this dashboard. So we have the alerts that are based on the water demand and the water use. Specific thresholds are being set. The user can also define those thresholds, and alerts will be presented to the end user when the values coming from the sensor measurements do not match those specific thresholds that we want. And to couple that, deep learning algorithms have also been applied to make better short and long-term water demand predictions and help further defining the alert and the nature of the alert for the user. Moving on, we have some pressure measurements, some historical data of pressure measurements. Again, the end user is given the option to choose the time period that he would like to see the historical data for, and also the sensors which correspond to this time period. So various sensors are being deployed throughout Braille, and all of them are being depicted in a specific map to have an overall view, but there is also the possibility to see individually historical data about each one of the sensors. Moving on, we have here the pressure and leak prediction diagram. This essentially comes from another component which is using the user-defined thresholds and the leakage and pressure parameters, and combining the data coming from the sensors, it makes some predictions about what is the lower, the average, and the upper forecast of any kind of water usage or spillage over the next few days, again for each individual sensor. And as Thanasis showed us earlier, there is also a weather forecast. This module is updated every 6 hours, and it gives predictions for the next 3 days. And this is what it looks like now for the end user when he wants to see what what the weather will be in the next hours and the next days. For every use case, there is a link to the water observatory. The water observatory essentially is a place which helps the end user by empowering him, making him more aware for similar issues that he might be facing, and giving the end user access to relevant indicators, media, research that has been done, or resources that might help him mitigate whatever issue they are dealing with. It gives essentially the opportunity to the end user to set up, based on their own needs, this part of the NAIADES project in order to be able to gain valuable information in time and get to know, as I said, the relevant events that might have occurred in the past in other similar infrastructures, giving valuable information on how to deal and mitigate any problem. And the last part that we have developed for the end users of NAIADES is the leakage detection map, where the end user here can see the original location of each sensor deployed and the status of those sensors. Again, there are some parameters that have to be fulfilled in order to say that each sensor is working properly. So there are also alerts raised in case of something happening outside of what is preferable. And the user, again, is being alerted on what the status of each sensor is. In case of a failure detection of some sorts, there is also a suggestion for a new location to move the sensor in order to keep the operation as smooth as possible and not have any leakage of water, or at least minimize the failure in the system. Moving on, we have the Carus Use Case. Carus is a city in Switzerland. Carus basically has two distinct pilot needs, let's say. One has to do with the watering of the flower boxes that belong to the municipality, and the other one is regarding the fountain that is in use on some specific months over the year in the city of Carus, which actually it is a very big fountain which can also accommodate people bathing inside it. And over the period of summer, it is very, very busy, as we have been told. And a lot of people do try and find some cool within this fountain. So it is very important for the end user to have a very good view of the water quality of the fountain at any given time in order to prevent any unnecessary happenings. ICCS, another colleague of ours within NAIADES project, is responsible for building the watering module, which gives the end user a dashboard of the city, which allows them to design their route, their watering route, more efficiently, and also gives them some indications about when it would be best to water what flower box based on the needs of each individual flower box, and also the weather prediction along with some other weather attributes that are expected for this and the next days. Finally, the end user can get a report with the actions that have ultimately been taking place. That is for the watering and for the fountain needs of Carus. This is the dashboard that the user sees. As we see, there are some distinct, let's say, modules appearing in the dashboard. We have some water quality measurements. Those are all coming from sensors that have been deployed within the fountain. There are also some forecasts regarding the water quality, where based on previous measurements, forecasts are being made for the water quality. Those forecasts are being used also as indicators when the actual data comes in. A juxtaposition is taking place, and in case of some big margin, let's say, or variation between what has been predicted that will occur regarding the water quality of the fountain and what is actually happening, the user is being alerted. And again, if there are some specific procedures or protocols that are taking place regarding a specific, let's say, alert, then the end user is also being suggested for the next courses of action based on their procedures and protocols for the issues reason. We also see again the weather forecast module, same as before, only with data relevant to the city of Carus. There is the option for a daily reporting. All the data that we see here, along with actions that have been taking place from the end user's part, are automatically saved and retrievable from the daily reports, so that the end user can have a day-to-day look overview and use it for their benefit. And also, we see a tab down to the right where any issues that arise will be reported there. So basically, let's say this is a placeholder for alerts for the user in order to take action. Okay, sorry. Yes. The end user can see historical data for each specific measurements of water quality, like pH, chlorine, turbidity, temperature, and others that sensors relevant to those have been deployed. The reason we see here a lot of straight lines is that currently the modules that provide this data to the main dashboard are being under development. So for those that are already in place, we're taking values. For those not, they appear to be giving only one specific value over time. This, of course, by the end of the project will look very different and have a historical value. Moving on, there is the option for the end user to add a new fountain. Should there be any such case, we wanted to give the end user the ability to add a new entity, given that it will operate in a similar way as the first fountain that we have been tackling with. Again, with some sensors deployed, looking for the same value, same water quality measurements, and combining the same kind of data in order to take appropriate decisions. We give the example of just by filling in those those four attributes here, and not by implicating any kind of developer in order to build a new dashboard to manage another entity as a fountain is. And this concludes with what the end user in Carus sees, and we're moving on to Alicante. Alicante's basic needs are regarding the water consumption in various points over the city, and what is the better way to ensure that there is no shortage of water in any place of the city of Alicante. So what we have done, we have built a dashboard where the end user can get some alerts on high and low consumption over various consumption points within the city of Alicante. There is some forecasts divided by sector, and they concern the next day and the water demand that is expected to be needed, the water that's expected to be needed for the next day. Again, we see that we have an upper and average and a lower forecast. Those schemas that we see, again, some of them are just placeholders waiting for data, since sensors have not been deployed or operational throughout the city of Alicante. Again, this is something that as we are closing to the end of the project, everything will become operational in order to be tested during our pilot case running. We also have a forecast for the next week, which is something very valuable for the end users, as Alicante does have a problem with shortage of water, and it is valuable for them to be able to have as much possible a better idea of what the demand for water will be over the next few days, because as they have told us, they are not just taking water from one place. Let's say they would have to be able to maneuver and request specific amount of water from various sources in order to fulfill the city's needs. So again, the forecast is presented in a similar manner with an upper, lower, and average forecast for the long term. And this module here would provide the historical data, as we have seen in the case of Alicante, a diagram with certain measurements that are of value to the end user. Again, the end user is choosing the time period that he would like to see the measurements for, as well as the kind of value he is looking to see depicted. This is what has been developed so far pretty much for the end users. Thank you very much for listening to me, and I will be happy to answer any questions that you might have regarding what you have just saw. Thank you very much.
Thank you, Nikos. And if any of you have any questions to Nikos, please write them to chat and we'll have time for them in the end. So our next talk is following on very nicely, and it's about NAIADES smart solutions for chloride predictions in water. And this talk is given by Mr. Cristian SALEMI, who is Technical Director at Ibatech, and he will introduce himself and the topic now. You're still on mute, Cristian.
Good morning. Sorry, I was mute. Thanks for introducing me to the webinar. Currently, I'm the Technical Director at Ibatech, in charge of integration engineering projects. We are going to present now some specific application developed under the NAIADES project. The title of the presentation is Smart Solution for Chlorates Prediction in Water. It's a very small application in comparison to the work we have done. In general, we have provided customized solutions to two sites, to Carus and to Alicante. In particular, in Carus, we were involved in the two use cases, the watering of flower bed and the water management in the public fountain. The overall goal of both was to decrease and optimize the use of water and to reduce the workload of operators. In Alicante, we were also involved in the use case to detect the intrusion of saline water in water plants, but we are focusing our presentation in the water management in the public fountain. So just to remind the presentation made by in the previous webinar, the fountain use case is a fountain in the Carus city, which is used by people as a swimming pool. And the problem was that there is sometimes accumulation of chlorates and bacteria, and there were the council was not able to predict these parameters in time, and there was not an early detection capability. So our solution was to propose an integrated sensor platform with a wide range of sensors, including the LoRa module for communicating with the already existing LoRa network in the Carus city. Inside this use case, we developed also a novel approach to determine the presence of chlorates, and this is the topic of this presentation. And also this use case approached the AI prediction model and other aspect of the use case that are approached by other partners. The problem was that the chlorates are present sometimes in the water of the fountain. Their concentration may increase as effect of the disinfection byproducts, for example, from chlorine dioxide or the sodium hypochlorite, and they have a negative effect on human health and environment. And there was not a capability to have an early detection, because they have to be measured by a sample taken from the fountain and analyzed in a laboratory. So as there is no method in the market for their estimation, we proposed a solution. The solution is to overcome the problem of taking the sample and bring the sample to the labs. And we developed a platform which included several sensors, for example, temperature, pH, free chlorine, total chlorine, combined chlorine as indirect measurement, turbidity, and in particular the redox or ORP sensor. And then the platform also included the IoT communication with the LoRaWAN network and a local data logging and local monitoring. We want to stress that the redox sensor is capable to measure cations and anions. Chlorates, like anions, can be measured by this sensor. Okay, this is the starting point of our work. The research objective were to reach a correlation formula to create a real-time indicator to predict chlorate concentration. And at the same time, we wanted to evaluate the production of chlorate as a byproduct disinfection, for example, from the chlorine dioxide or sodium hypochlorite. So our approach was divided in 5 main steps. We are going to analyze one by one what we did. So the method 0, we just used distilled water and used several concentration of chlorates, and we recorded the response of the sensor and analyzed statistically the values and came out with a correlation formula. In the second stage, method A, we analyzed the chlorate production due to the sodium hypochlorite degradation within a period of 7 days. The idea was that the more the sodium hypochlorite in water, the more the hypochlorite ions, and consequently more probability that the hypochlorite ions will degrade into chlorate according to the formula shown in the slide. We used concentration which were above the normal concentration of hypochlorites and chlorates in the normal swimming pool or in the fountain. So we analyzed this process of aging with HPLC lab instruments. And also in this case, we came to a correlation formula. Then we did more or less the same, but we added at the beginning of the aging a little concentration of chlorate, because we suppose that the chlorate can act like catalyzer of the production of more quantity of chlorates. The process is very similar to the method 1, but in this case only 5-day periods. And also in this case we reached a correlation formula. Then method C was split into 2 different methods, CA and CB, which actually were emulating the previous method A and B, but with concentration of sodium hypochlorates and chlorates in the range that are expected in the fountain of Carus. So also in this case, we came with two correlation formula. After all this work, we analyzed the data, and we see the lesson learned. The method 0, we had a good response of the system to the chlorates. It means that especially the sensor ORP or the redox was able to correlate and read the presence of chlorates ions. Anyhow, the overall output and the correlation formula obtained was not consistent for the NAIADES applications. In method A, B, and C, we see that in laboratory, with stable condition, it means without solar radiation and with minimum diurnal temperature variation, the aging of the sodium hypochlorite over a period of 5 or 7 days and its conversion to chlorates is not significant, even with a high initial concentration of chlorates. The reading of the sensor for free chlorine and total chlorine are directly related to the overall concentration of the sodium hypochlorates, and the concentration of chlorate are not significantly detected by the fountain sensor. Despite the wide measurement range of the redox sensor, which can measure from minus 1,500 to plus 1,500, all the measurement in all the method were very small. The observed variation of this sensor was generally in the range of a few units for method A to maximum a couple of tens to method B, and maximum 3-4 tenths for method CA and CB. The ORP sense measurement decreased slightly with the increase of chlorates and decrease with the increase of sodium hypochlorates. And also the initial value of the variation of ORP sensor is more related to the sodium hypochlorate concentration than to the concentration of chlorates. More in detail, chlorate concentration generally increase inversely proportional with the concentration of free chlorine and total chlorine. This is apparently due to the mass balance. It means that the mass losses from the bleach concentration is equivalent almost 100% to the concentration of chlorates in a period of 5-7 days. But we have to say that this change is not significant. The behavior of the redox sensor is quite steady, like the tendency of the value of pH and temperature. And it was also found that the ORP, the redox sensor, the free chlorine sensor, and total chloride sensor were also quite sensitive to the water composition of anion and cations. It means that it was important to work with the real water. So the real conditions, we means solar radiation, temperature variation, and organic compound in water have a clear influence in the outcome obtained, and in conjunction with the composition of the water may play a catalytic role in the production of chlorates and consequently affecting the estimation formula outcomes. So after analyzing all this data and coming with this result, we understood that what we have done was to work with a laboratory simulated water. we took the composition of the water of Carus, and we recreated the same composition in the laboratory, and then we played with the chlorate concentration, hypochlorate ions, and so on. But this was not enough, and the overall result was affected by the quality of the water itself. So in the next stage of experimentation, we asked it to use real water. So we took one sample a day during the period of 1 week, and then we analyzed in the lab, and then we correlated what our system was measuring, downloading the data from the NAIADES platform with the results obtained in the lab. And then we came to another formula for the prediction of chlorates. And what we did then was to apply this formula to the data downloaded from the NAIADES platform since July 2021 to October. And what we can see is that the prediction model is quite coherent with what expected by the real situation. The concentration of chlorates are very coherent with the expected result in the real laboratory analysis. So what we can conclude is that this application, which take in consideration the specific surrounding conditions of the water, including its initial composition, is feasible to be used to be extrapolated for other similar applications. That's all for my side. If you have any question, happy to answer.
Thank you, Cristian. And this concludes the session 1 about NAIADES project. And if you have any questions about NAIADES project, any of the talks, or if you want to ask anything about NAIADES project in general, feel free to drop all the questions to the chat. And now the session 2 is the first talk is given by Dr. Brett Snider. She's representing project Aqua 3S, and he's a postdoctoral researcher at Center for Water Systems at the University of Exeter, and focuses on building water system resilience through real-time detection of crisis events through data analysis. So whenever you're ready, the floor is yours.
Hi, everyone. I hope you guys can all hear me. So yeah, hi, thanks everyone for coming to this presentation, and thanks.
Sorry, the microphone is very quiet right now.
Oh, okay. 1 second. All right, how about now? Is it better? Can you guys hear me?
It's much better. Thank you.
Oh my gosh. Oh, can you guys hear me? No.
All good now.
Oh, it's good. Okay. Sorry, sorry for that issue. Yeah, so as I was saying, thanks for giving me this opportunity to present today. My name is Brett Snider, and I'm going to be talking about a comprehensive leak detection system that we've developed for the Aqua 3S project, as well as for the Fireware for Water project. So as many of you guys are probably well aware, there's a variety of issues facing water distribution systems in the 21st century. One thing specifically that I've been focusing on is pipe bursts and the deterioration of water infrastructure. Many of the pipes have been installed for several decades, and they're starting to deteriorate and reach a point where a large number of these are starting to fail much more frequently. One example is that in North America, some studies suggested that pipe breaks are increasing about 27% in the last 6 years. And there's other studies that are suggesting maybe not as aggressive, but similar increases in Europe as well. And so the impact from these pipe breaks can be severe and impact water quality and nearby infrastructure, et cetera. And so being able to respond and mitigate these impacts is crucial. And so there's a variety of tools that have been developed in recent years to try to improve this. Specifically, what we're going to be focusing on today, and what I've been focusing on in my research, is improving sensor detection systems so that we can respond quicker to pipe bursts and mitigate their impact more effectively. So we've developed a comprehensive leak detection system. So here, many leak detection models may not have all these steps, but we've developed a three-step approach. This would be first to detect the leak. So this would send a leak alert if we notice some anomaly in the sensors. And then the next step would be to locate the leak and identify the location of where the leak is most likely occurring, and then response and determine the most effective response for the leak. And so this would be determining which valves to close and to isolate the leak, and maybe opening up certain valves to reduce the impact on nearby infrastructure, and to respond most effectively and reduce the impact. So today, though, I mean, to focus on each one of these models would take some time. So today I'm just going to be focusing on specifically the leak localization model, as it's probably one of the most critical and time-consuming as well. So if we think about leak localization, a water distribution system can be very large, and having sensors spread out throughout the entire network at very small increments would be very expensive. And so instead, what we're often left with is wireless sensors that are spread out more sparsely throughout the water distribution system, and identifying where the leak is occurring within these distribution system can be more difficult. And if we're able to locate the actual location of the leak, this can reduce the search time required, and we can contain the event much quicker. And so this is what leak localization models are focusing on. So most of the leak localization models developed today focus on identifying a specific location. And so if we think about it, there's a variety of these models. So one would be the classification machine learning models, which identify a specific leak node. And then there's other ones that identify a specific latitude and longitude, which is typically done through regression machine learning models. However, leak detection crews are still required to be sent out to confirm the actual leak location. And so when these leak detection crews are sent out, and if they're not at these exact predicted areas, the leak detection crew is often left wondering where to go to next. And so this is what we've really focused on trying to improve. And we wanted to identify specifically a search area for the leak detection crew that it has the highest probability of containing the leak. And so we did this through applying the maximum coverage location problem algorithm. And so this maximum coverage location problem algorithm was created a long time ago by Church and Reval in 1974. But in recent years, it has gained a lot of attention with the advances of geographical databases. And so the maximum coverage location approach analyzes specific search locations, search radiuses, and predicted probability to identify the specific search locations that maximize the probability coverage. This is all to say that it identifies the location that is going to most likely contain the leak. So if we think about it in this diagram here, if we think of the nodes here, these blue dots as nodes within the water network with predicted probability of the leak occurring from the machine learning model, the larger the node, meaning the higher probability, the maximum coverage location problem searches through possible search areas, giving a specific search radius to identify the maximum coverage, and so therefore the most likely containing the leak. So by applying this to this approach, we've developed an entire localization methodology. And so here we can see that it's a model-driven approach. So we use a hydraulic EPA net model to calibrate the localization model. So specifically, we run a normal non-leak scenario is simulated, and then we add noise to the demand and sensor readings to reflect a more realistic scenario. And readings at the sensor locations are recorded. So either the pressure or the flow sensors in this case. Leaks are then simulated using a pressure-driven analysis in the hydraulic model, and the sensor readings again are stored. We calculate the residual vectors, simply just comparing the leak scenarios to the normal scenarios. And we use these residual vectors to train and calibrate the machine learning model. So here we're using a random forest model, but a variety of machine learning models could be applied. And so this machine learning model, so we use this approach to calibrate the model, and then the machine learning model predicts the node probability, so the likelihood that the leak is occurring at all nodes within the network. And then the maximum coverage location problem approach is used to identify the ideal search locations to cover the maximum probability given their user settings, so the search radius or the number of search areas. So to analyze the impact of this and to determine the effectiveness of the maximum coverage location approach, we used a case study. So this is a case study from a UK water distribution system, and we simulated 13 sensors across the water network. And we used a test set of 200 leak scenarios, an independent test set. So this is separate from the training data sets. One of the major benefits of the maximum coverage location approach is that it's very customizable. So the number of search areas or the search locations and the grid spacing can be defined by the utility. And so we wanted to analyze the impacts of these various inputs on the accuracy of the maximum coverage location approach. So here we just provided a sensitivity analysis. And so here the grid spacing, what we're referring to in the grid spacing is the locations for the search area centroid. And so if we think about it, the maximum coverage location approach simply searches through a variety of search locations. And if the grid sizing was smaller, it means it would search through a larger number of them. And so as you can see, as the grid size becomes larger, the accuracy, the leaks detected decrease, but the computation time decreases. So it's a trade-off between computation time and the leaks detected. The other and maybe more important parameters that we analyzed were the search areas and the search radius. And so again, this just is highlighting the customizability of the maximum coverage location approach. So if we think about it, as the search radius increases or the number of search areas increase, the likelihood of leaks being contained within these search areas increases as well. overall, though, the sensitivity analysis just highlights the customizable approach of this, and utilities can then do further analysis to determine the number of search crews that they would want to be able to respond effectively to a leak. They can also even further analyze to determine what impact another sensor would have on their ability to respond to a leak and capture the leak quickly. Lastly, we wanted to determine for sure if that the maximum coverage location approach actually reduces the search area required by the utility. And so we analyzed a variety of other leak localization approaches that have been developed in literature to determine if the actual search area is reduced. And so we compared with 3 other models. So we looked at the classification model, which predicts the node with the actual highest likelihood of the leak occurring within it and expanding the leak out or the search area out. So if you think about it, if a crew was sent to that search area, where they would search the radius further out from that location until it captured 50% of the leaks within the test data set. And then we did the same for a regression model. And then we analyzed a clustering model as well for 2 search areas. And what you can see is that the maximum coverage location approach actually reduces the search area substantially. So the maximum coverage location approach with 1 search area reduces the search space compared to regression by 35% and almost 50% compared to classification. And then if you look at the maximum coverage location approach for 2 search areas, it reduces it almost 80% to regression and still outperforms the clustering model as well. So these results highlight that the maximum coverage location approach significantly reduces the search area required for the leak detection crews, which also can be considered and applied to the ability to respond quicker to the leak. So I think just in general, though, when developing these leak detection models, we need to consider the utility's end use, and specifically that the leak detection crews are still going to be required to confirm the actual leak location. And so if we can develop leak location models that substantially reduce the leak search area, for example, in our case, through the maximum coverage location approach, leak detection crews can reduce the time of the leak running and reduce the impact of the leak. The other thing I think that is very important is that utilities have a variety of needs and abilities. They may have only a certain number of search or leak detection crews, or they can only search, or they need a requirement of searching a certain area in a certain amount of time. And so having an approach that is very customizable is very important. And so in general, that's the leak localization model that we've developed to date. We're going to continue working on improving this model and integrating it into a visual dashboard and assessing it with real sensor data in the short future. Thanks, everyone. That's it for now.
Thank you. Thank you for presenting this very interesting topic about water leaks, and the percentages were very high because I didn't have any knowledge about this before, and like reducing the search area by 80% seems a very significant improvement for this model. So thank you.
Thanks.
So our next presenter is also from the same university and research center, so Center for Water Systems, Mr. Gareth Lewis. And he's presenting the fiber for water project, and he will further introduce himself.
Thank you very much, Tilly. Hello, everybody. Can you all hear me all right?
Yes, all good.
Excellent. Okay. My name is Gareth Lewis. I'm also a research fellow at the Centre for Water Systems at Exeter University. And Brett and I work together on the same projects. And we wanted to use this session to really look at water event detection holistically. So Brett's looked at the actual mechanics of event detection for supply-side leak events. And I'm going to look at what happens to customer-side leak event processing as a kind of broader business, in a broader business kind of operational context. So effectively, this should be a top-down presentation to go with Brett's bottom-up presentation. So to do this, I'm going to use our work with Southwest Water on the Fireware for Water project. So it's a different project to the project that Brett was talking about, but there's a lot of crossover. Fireware for Water is a multi-pilot research program that works across 4 pilots, considering the role of smart solutions across the water life cycle, using Fireware Smart Solution Platform to provide a common and reusable and potentially open platform for the collection and management of water data. Sorry. And Southwest Water's involvement on that project is concerned with smart metering and citizen engagement, though I'm only going to concentrate on the smart metering side of the project for this presentation. So Southwest Water is a privatised water company in the UK, and it's subject to Ofwat, which is the Water Services Regulation Authority. As part of those regulations, UK water companies are committed to a 5-year plan to reduce leakage by 16% and a longer-term follow-on plan to commit to reductions in consumption leakage. So we can see that as far as the UK water system is concerned, companies are very much tied to this long-term goal of reduction of leakage. Typically, leakage occurs in 2 areas, and like Brett was saying, it occurs through infrastructure failure, and secondly, through customer-side supply issues. And what you tend to find here is that the leaks in the distribution network are often very easy to spot. On the left here is Brent Cross from 2020. This was a leak just under the North Circular, which is one of the main arterial roads in London, and that's very easy to spot given the instant lake that it created. Conversely, customer-side leaks, and I've got an image here on the right of a water leak behind a wall, tend to be far more difficult to spot because generally customers aren't experts in leak detection, and the whole leak kind of ownership and management issue in the UK can be very problematic given the demarcation between customer responsibility and supplier responsibility, as seen here in the bottom right, which is an image from South East Waters showing you the responsibility that you have as a customer. Oh Christ. So traditionally, dumb water systems are used to record total water consumption, and this data is collected through manual readings once or twice a year. And while this gives some insight into consumption, that there's little or no opportunity to detect customer-side leaks, and this often leads to long-term leakage issues. To give an idea of the scale, the Leaky Lose program it is a response that Thames Water developed several years ago to reduce leakage from dripping and leaking toilets. The estimates they had there was that typically a toilet leak could be around 400 litres of leakage per day, compared with typical per user usage of around 100 to 200 litres a day. And the worst case they found was 8,000 litres per day. So although customers don't generate the same kind of floods as the North Circular, there are a lot more customers. There's a lot of scope for leakage. The opportunity here with smart metering is that smart meters provide functionality to capture daily consumption data and phone at home for daily analysis. And they give water companies more insight into consumption and the changing patterns of consumption. This is helped greatly by smart meter features such as flow persistence or continuous flow, which will raise an alarm on the meter if the meter doesn't record any period in a day where there's no flow recorded. And this information would be highly meaningful into customer-side leaks, because the definition of a customer-side leak is effectively a continuous flow over 24 hours. For Southwest Water, this is the how side of event detection. We can install meters into customer properties, and they will capture daily leak event information. We then need to consider what we're actually going to do with that information. From Southwest Water's perspective, you don't simply move to smart metering. It's a substantial operation. Within the Southwest Water catchment area, there's around 2.2 million people, which equates to about 500,000 properties. So it's a large undertaking. The Fireware for Water project gives Southwest Water the perfect vehicle to be able to learn about smart metering in a controlled manner through the establishment of a pilot scheme, and develop partnerships with domain experts in digital resource management, which are the Fireware Organisation, EGM, and Exeter University, which should help reduce the inherent risks and unknowns of such a programme. So to realise this pilot, Southwest Water chose Great Torrington, which is a relatively small village in North Devon. It's got a population of about 5,000 and around 2,000 meterable properties. They installed around 100 metres and constructed an associated over-the-air network, which would allow meters to wirelessly send data to a Stelio context broker operated by EGM. One of the things that's very interesting about Great Torrington, and something that made it a very useful pilot site, was it has a mixture of properties. And the installation process, or attempted installation process, demonstrated that installation was not necessarily easy or possible for some of the older buildings, and the two images here in the middle are kind of typical Torrington 17th century housing, which clearly weren't built for smart metering. Likewise, the over-the-air network between the smart meters and context broker demonstrated that while data collection was generally good, it was not 100% reliable, which kind of mandated the overall data processing model needed to consider missing data and provide suitable infill where possible. I've got a diagram here of a typical context broker configuration, and we're using Stelio as a context broker to form the hub of the data service, where microservices can connect to the broker through the hypertext HTTP protocol and request and update data on demand. So on the left-hand side, data is captured from smart meters and transformed into a format called JSON-LD that enables it to be stored in the Fireware model standard. JSON-LD is human readable, as you can see on the left, so it's relatively easy to see what's going on with the data. And it's built off the industry standard JavaScript object notation format. So we have a well-established, well-understood, and well-tested data format that's easy to work with. Doing this allows applications to share data and use common models as part of the open system of Fireware, but data doesn't need to be made open to all. So there is still privacy for the data that's being collected. And the data that's built from the smart meters is then collected with the IoT agent and stored in the Stelio broker using HTTP requests. For the Southwest Water pilot, we've got two applications on the right-hand side, an application for customers and an application for the Southwest Water leak operators. And you can see here that they're both using the same data sets from Stelio. So it makes it very easy to give everybody a common data format, so nobody's surprised by the data they're getting. Now, once stored, the data can be accessed through HTTP requests, and it allows a range of applications to share data from the Stelio broker. I've got a couple of results from the analysis processes I've been running. These are back-end, and they're not for users or consumers, so I'm not expecting this to be presented to anybody outside of myself, really, as a developer. On the left-hand side, I've ranked all of the meters by actual meter readings over a period of around 5 weeks. So on the left-hand side is 22.1, which is January, and then 22.2, which is February. What we can see underneath is the X's indicate actual data collection, and the E's indicate estimates. So these are days when the over-the-air data collection failed. And what we can see here is that while pretty much all of the meters that are presented have got a very good ratio of data collection. There's only a few gaps. As we move down to about halfway, we've got a meter here where pretty much every couple of days is a failure. And that can be incredibly useful because it then means that there's scope to be able to address aerial location and assorted technical stuff to make sure that we get better recordings. On the right-hand side is the really important data from our perspective. It's flow persistence over time. And again, I've ranked these by worst to best flow persistence. So that the one at the top, the X indicates a flow persistence alarm. So we can see the topmost meter is producing 100% flow persistence. So that's kind of indicative of an ongoing leak. And then as we go down, there are more blank days, which suggest no leaks. And here we can see we've only got 5 that are generating leaks. And the 5th one down here is only a leak for 3 days. So that may well be somebody leaving a tap on or something quite innocuous, whereas the one at the top is probably something quite serious. And this is exactly the kind of information that we want the smart meter leak detection to bring out. I move on. So the results we have today is kind of interesting. At the moment, we're still in the middle of developing the software. We've not quite rolled it out to the consumers or to the Southwest Water leak operatives. But what was particularly interesting was that the projects enabled Southwest Water to build relationships with its customers in Great Torrington. And this has led to kind of 4 key outcomes. So the first one is identification rectification of 4 large customer leaks. So like I was saying earlier, typically a user will use about 100 to 250 litres of water today. So for the 4 large customer leaks here that are using 1,000 litres of water, that's effectively 1 property's worth of water. So instantly, without doing anything, just by going to see customers, Southwest Water has reduced the consumption in this region by 1%. Secondly, there was a large commercial leak around 2,500 litres a day. So that's like removing 10 users from the water system. As part of the preparation for the smart metering network, Southwest Water made a set of water efficiency visits, and they had 344 of those over the customer base for Great Torrington, and that saved an average of around 60 litres per customer. So again, 100 to 150 litres of usage per day. That's a substantial reduction. And from the customer's perspective, 70% of smart meter customers are saving money in comparison to using dumb meters, and we've got an average of just over £300 and a largest of nearly £1,000. So I think what's very interesting with these figures is it shows that for water companies, just engaging with customers and not actually doing anything, not installing the smart meters, is enabled significant reductions in leakage to occur. Once we have the leak detection software in place and the leak units actively cover leaks, that should reduce it even further. So thank you.
Thank you, Gareth. So our next presentation is also from the same project. So Fireware for Water, and this is given by 2 presenters. So Dr. Stelios Samios and Mrs. Vasiliki Polychniatou, and they are from EYDAP, and they will introduce themselves and their topic further.
Hello, my name is Stelios Samios, and I'm the head of the R&D department of EYDAP. Next to me is Vasiliki Polychniatou, who is a research associate. And actually, Vasiliki is the project manager of Fireware for Water in Athens in EYDAP in Greece. First of all, let me tell you a few words about EYDAP. The company we are representing, EYDAP, stands for Athens Water Supply and Sewage. Is the largest company in Greece active in the distribution and management of water, and also the provision of sewerage and wastewater treatment services. As it can be seen, EYDAP supplies Attica, I mean the region of Athens, with some of the highest quality water in Europe. It serves about 4,400,000 customers. The length of water pipelines is 14,000 kilometers, and the sewerage sector serves 3,500,000 residents. The length of the sewers is about 9,500 kilometers. No problem. Well, the main water supply sources are the lakes of Mornos and Evinos. Actually, they are not exactly physical lakes. They are reservoirs used in pristine areas. They are located in pristine areas free from agricultural and industrial activity, so that the Greek capital city is supplied with water of excellent quality, transported by gravity, so with very low energy consumption. Based on current operating conditions, EYDAP water sources can be divided into main water sources, Evinos and Mornos reservoirs, auxiliary water sources, Eliki and Marathonas, and backup water source, that is the underground water. The quality of the water resources is monitored according to the Directive 75/440 EEC for surface water quality standards, and National Healthcare Provision of A5/2080/1983 by random checks of the water quality in the reservoirs. We can see now the external water network, that the transfer, you can see that the transfer of raw water sources to the water treated plants of Attica is accomplished via an extensive external aqueduct system with a length of about 500 kilometers. I remind you that it is transported by gravity. Constant monitoring of the external aqueduct system operation is, of course, crucial for EYDAP, because we must ensure and certify the excellent quality of water and services that must be provided to the citizens of Athens. That's why daily quality control tests of the raw water must be conducted, and they are conducted with cutting-edge analysis methods in the chemical as well as microbiological laboratories of EYDAP. In addition of that, state-of-the-art systems for the online monitoring of qualitative parameters have been installed at crucial positions at the external aqueducts that can send real-time results with the use of telemetry and timely notifications in case of extreme rates. We can see from the map the exact points where we have quality stations, water level meters. Actually, we have 13 water quality stations, 73 water level meters, 20 flow meters, 38 water gates, and 34 pumping stations. Currently, the monitoring is performed these installed sensors. Okay. So the Athens demo case that refers to 5W for water, EYDAP, along with University and TUA, are responsible for this demonstration of 5W integration with existing operational sensors and other novel surveillance methods into a common operational picture in real time, in a suitable part of the external water supply system. The overall goal is to upgrade the supervisory system and digital water strategy of the company. We had to face some challenges. The challenges were the integration of different sensors from different vendors into a unique operational system. The other challenge, the development of different applications, models, and analytics that will interface with and provide added value to the legacy systems, sensors, and online control systems. So, please, I would like to ask Vasiliki to continue with details.
Thank you very much. So, firstly, in collaboration with NTUA, National Technical University of Athens, we identified the use cases in the form of specific user stories in terms of water flow and water quality management. And thus, 2 5W compliant web platforms were designed, covering the quantitative and qualitative aspect of the raw water conveyance system. The water quantity platform was designed to monitor in real time the flow conditions in the conveyance system, obtain information on the flow at different parts of the system and different time periods, and supervise the operational conditions of sensors across the entire aqueduct. The platform can improve the response of EYDAP staff to unusual flow conditions by raising warnings when an abnormal event is detected. It can also provide information on potential water losses from the conveyance system and estimations of future demand volumes. It is essentially an advanced decision support system that provides advices on an optimal settings of sluice case, so as specific flow conditions to be attained in the conveyance system. Oh, sorry. Moving to the second 5W compliant platform, the water quality platform. It was designed to monitor in real time the water quality of raw water at different parts of the system. The platform provides also access to historical data, which can be processed and analyzed via advanced smart analytics to provide meaningful insights on the qualitative regime of the conveyance system. The platform also contains a real-time early warning system to inform in advance for unusual quality events in the conveyance system, along with the time needed to reach the treatment plants, allowing thus the staff to make the suitable preparation in time. Sorry, again. So after the completion of 3 productive workshops with NTUA, we identified the current state of the legacy system and the specifications of the demo. Particularly, we specified the demo part of the aqueduct, which is Giona Dafnoula, which covers a total length of 131 kilometers. Then we identified the legacy sensors already installed in the demo part, which are 5 open channel flow meters, 46 level meters, 8 sluice gate sluice gate opening valves, and 6 water quality meters. Then we proceeded on the documentation of the characteristics of all metering stations and physical elements of the conveyance system, as well as the existing information systems of EYDAP. We then moved on the collection of historical data from already existing sensors. And finally, we decided on the new sensors and systems that should be deployed to enable the development and operation of new tools, specifically what-if hydraulic scenario assessment for optimal water conveyance and real-time water quality early warning application. As I said, more points were needed to be monitored to enhance the hydraulic model accuracy. So in March 2020, we finalized the installation of 5 level meter stations, and in December 21, we proceeded with the application of 1 portable open channel Doppler flow meter at the demo part of the company's external water supply system. The data derived from the new meters were integrated with the data from the existing operational meters, of course, and subsequently, 5 were compliant analytics and models were used to synthesize the information and provide operational decision support. NTUA, on the other hand, developed the 2 5-ware compliant smart platforms that I mentioned before, that can support the real-time monitoring and operational management of raw water conveyance system of EYDAP by integrating data from all the existing sensors in the demo part of the conveyance system. The prototypes for both water flow and quality applications are currently in a live environment, receiving real-time data in the context of 5-ware compliant analytics and models. Additionally, an SC system, which is an information system developed by NTUA, was configured to integrate into a common operational system real-time data from flow meters, water level meters, sluice gates, opening meters, and water quality sensors. The 2 distinct dashboards have been set in motion to provide feedback to the relevant operation staff in EYDAP. And the homepage of the platform provides a quick access to real-time data, either by water quality or water flow dashboard. Oops. Sorry. So something a little bit different now. In the context of 5-ware for water, EYDAP also took the initiative to create the first Athens Water Forum. With the goal was to create a group of organizations and individuals interested in water issues in the city and open the discussion on the most important natural asset of the planet, which is water, of course. We carefully formed a partnership with several Greek organizations that are sensitive about water challenges at the Athens region, such as the National Technical University of Athens, the Global Water Partnership, the Municipality of Athens, and others. I have also to mention that the Athens Water Forum initiative is supported by the United Nations World Water Quality Alliance, which create networks of people and organizations from around the world who jointly set up and implement new ideas around water. Since the creation of the forum, the partnership decided on specific water issues and opened a dialogue with the public through a targeted audience survey. We circulated the digital, in particular, we circulated a digital questionnaire from January 10 to 21 of 2022, the members of the Athens Water Forum networks, to investigate and classify the interests of citizens around water in Athens. Surprisingly, we received 348 responses, and 198 of them expressed their interest to participate in the following events that we are organizing. And our next steps for the coming period is to organize 2 open-air citizen engagement activities by May 22, which is when the 5-ware for water ends, which will foster dialogue on water, the environment, climate change, and other issues identified in the city, while enhancing active citizen participation and cooperation. Thank you very much. That's the end.
Thank you to both you, Vasiliki, and to Stelios as well for the presentation. And I'm very happy that you have almost 200 people waiting for your next events. That's very exciting.
Yes. We were also surprised, to be honest.
It's always best to be surprised in this way. Excellent. And we have come to our final presentation before we have time for questions and discussion. So our final presentation is from digital-water.city project, and is given by Serena Radini, and she's a PhD candidate in the field of chemical, environmental, and sanitary engineering.
Hello, everybody. I'm Serena Radini. I'm a PhD student at the Polytechnic University of Marche, and today I'm going to present a digital solution to early warn and support decision for safe water use. This digital solution is developed under the project digital-water.city, that is an Horizon 2020 project. And its main goal is to link the physical and the digital world along all the value chain, addressing water-related changes by developing 15 digital solutions. And one of these solutions is at wastewater treatment plant level, and is the early warning system for water use that is developed in a case study of the peri-urban area of Milan in Peschiera Borromeo wastewater treatment plant. So the aim of the early warning system for water use is to control, monitor, and share with stakeholders and final user all the health risk related with the reuse of treated wastewater, maximizing the benefits of effective water use in productive agriculture. So the tool is a risk-based decision support tool, and it uses both data, real data from the plant, both offline data and real-time data from sensors network that are installed in the plant, but it uses also simulated data and generated data from statistical correlation. The main quality of the tools is the ability to monitor and control the process of wastewater treatment. So it elaborates the data that it received, and it can evaluate water quality. So it can provide a green or red light for water use. But it's also a tool to support decision-making, since it can be integrated to enhance and optimize process control. And finally, it's a tool to support risk management, because it will be integrated inside the risk management plan. And so it will be a control measure to minimize risk related especially to health issues. The case study is the Peschiera Borromeo wastewater treatment plant that is in the peri-urban area of Milan. So there is the wastewater treatment plant that is already equipped with the monitoring network of sensors. And inside the project, innovative sensors were tested and installed, especially to monitor and detect E. coli concentration along the treatment drain. The irrigated field with treated wastewater is near the plant, and is also monitored with field sensors. During the first phase of monitoring data, we found that there were many issues related to the reliability of sensors data. And during the test for E. coli contamination, we found that the bacteria contamination was strictly affected by the presence of suspended solids. As we can see here, the reliability of the sensors already installed in the plant was very low. So compared with the lab data that were obviously considered more affordable, the probes had a very wide bias, and only limited time series were comparable. So we decided to make the architecture of early warning system using both data from wastewater treatment plant, but using also data from model simulations to support increase the number of the data available, and also to develop simulations that could simulate malfunction scenarios in order to increase the numerosity of our data set. So we use those data to feed an artificial neural network that is the core of our early warning system. And this artificial neural network will provide us the evaluation of specific output parameters that we selected as the total suspended solids, but we can find also BOD or COD that are other parameters that are not measured by sensors. And it can also predict the wastewater treatment plant performance, and both in using soft sensor and using prediction. So it can be applied for the early warning system. So the support from modeling came first to increase the numerosity of our data set. So simulations were carried out and validated using lab data from the wastewater treatment plant obtained during the normal conditions in different seasons of the year. But this data set was implemented generating new data related to extreme events. So we simulated different malfunctions of the plant to introduce risks event, hazardous event, in order to obtain simulated data. Those data was first fed to the artificial neural network. So here on the left, we can see the data that we used to feed the artificial neural network, and we can see that are almost common data that can be detected by sensors commonly installed in almost all wastewater treatment plants. And what we aim is to find the value of the effluent suspended solid that can be correlated to the presence of pathogens or bacteria. As we can see, using simulated data, the ANN was able to predict the value of the suspended solids. And finally, we trained this artificial neural network, and we revalidated this unit using a domain readaptation. So we used the same ANN, but this time using real sensors data. And we can see that as the same, we can have a good correlation between the measured TSS and the predicted ones by the model. So this is a model that can be used to predict soft sensor, and that can be helped through risk assessment and risk minimization, especially in those case applications that require specific control measures, such as the reuse in wastewater, the reuse of wastewater in agricultural applications. And that is, thank you.
Thank you a lot, Serena. So we have come to panel discussion and questions. We have quite a lot of time remaining for questions, which is great. So if any of you have any questions, then write to any of the speakers, both from NAIADES side or presenters now. You're very welcome to either submit them to chat so I can read them out, or if you want, you can unmute yourself and ask a question if you want to. But while I think, I'll ask the first question myself, and if any other come in, I can just use them as well. So I would just come back to you, Serena, and ask, like, how did you choose or select which data to feed to your artificial neural network?
Yeah, we selected the data considering which data could be most easily found and measured in a common wastewater treatment plant. So we selected flow rates, we selected effluent parameters that could be measured by sensors such as nitrates, phosphates, or ammonia, the pH, or parameters that are measured inside the unit processes, such as the dissolved oxygen or the temperature, in order to be as much flexible as possible, so considering the possibility to exploit these results in other case studies.
What are your thoughts? What other case studies could this system be used?
There can be other wastewater treatment plants that maybe both wastewater treatment plants that want to implement water reuse, but also for wastewater treatment plants that want bigger support to process control and monitoring, so they can maybe ask the implementation of an early warning system just to detect and monitor the operations and detect wastewater quality to see and control the efficiency of the treatment processes.
Thank you. I will just ask a few more questions then, if no one else has questions, because I have loads of questions to everyone. So maybe going back to Brett about finding which area to look for the leak. So how would this approach with defining various zones and looking for the leak in them work if you already have predefined zones? For example, I think in the city there could be 2 companies or water suppliers maybe. If you're speaking, I can't hear you.
You guys hear me now? No?
A bit quieter, but yeah, I can hear you now.
Okay, I don't know. Sometimes my headphones have been causing some issues, but I'll try to talk louder. Oh, no, that's not it. Okay, so hopefully you guys can hear me. Yeah, I think the one way of doing it would be to either train a specific model for that DMA, so you could then predict kind of hotspots or specific areas that could prioritize the search within that DMA or within that zone. The other thing, though, is that further research that we're doing is comparing if it wasn't a DMA, if it was just specific zones that they had already divided up for no specific search detection purposes, it would be interesting to compare that approach. So a clustering before prediction versus the MCLP approach after prediction. And so that's the other research that we're doing right now. So we don't have those results yet. But the one way would be to just have individual models for each DMA to highlight and prioritize search areas within that DMA, if that makes sense.
Yeah. I'm excited that you're ongoing with this research, and it seems like really up there. So the answer isn't known yet, and it could be really beneficial. Yeah.
Yeah.
But are there any other systems apart from water leak detection where the similar computational model could be applied to?
Yeah, I think I've been thinking about this, and I think there's a variety of systems. I mean, first of all, it could be applied for water quality as well, not just leaks within water distribution systems. But going even further, I think any system that's aided by a model to predict specific nodes in the location could use this approach. So I think sewers and stormwater systems could easily adapt this approach to detecting blockages or breaks or possible contaminant entrances. And so I think, yeah, the application of this approach to sewer systems and blockages where crews are still needed to be sent out to identify the location of the blockage, it could adapt this approach, and I hopefully it would save them time as well. So,
yeah, thank you. So I have a question about EYDAP demo case in Fiverr for water project as well. So what were the main challenges or the challenges that you're still tackling in the project?
Hello again. So the main challenge was that we had to different sensors. We're currently submitting and storing data in proprietary subsystems in EYDAP with different information systems installed. In the unique information system, this was the problem that we had, and we had several difficulties interfacing everything seamlessly. But thankfully, we found a way to overcome this. Yes.
That's great. Yeah, proprietary software combinations can be very challenging. And I guess this could be one of the blockage in the way of smart water and innovation in the wider sense as well.
Yes, exactly. And actually, it's a common problem that most of the water utilities have, because their legacy systems are of different ages, different technologies, and that's why it is so difficult to have a uniform interface.
And do you already know, or what is the main innovation that you have already achieved in the project?
Yes, sir. It was this achievement actually that we had everything integrated, and also it was the development of the operational decision support system for the improvement of the raw water flow and the quality management.
Thank you.
You too.
Any questions from anyone else? Still no?
I would like to post a question, if I can. I don't know, since I'm supposed to be asked the questions. However, I wanted to talk to our colleagues, to Vasiliki and Stelios, about something that's mentioned now. I wanted to ask about the decision support system that has been developed. And this is a curiosity question, because we are also developing a similar system. What is the value that an organization like yours is looking to? What's the benefit that an organization like yours is looking for in a decision support system?
The benefit, I mean, it's mostly consulting, of course. The staff gets the advice that the decision support system generates, and we use it as a consulting tool. We haven't incorporated it in the operational system. It doesn't change the operation of the flow of the conveyance system.
Okay, I see. So this helps the better management, let's say, of the processes involved, which leads to the benefits of a better resource allocation, let's say, or less water spent or less effort spent in any case.
Yes, exactly. Sorry, I think that I hadn't understand your question. Yeah.
Okay, thank you very much. And thank you for giving me the opportunity to ask a question.
Thanks a lot, Nikos, for asking questions, because all the speakers are welcome to ask questions as well. But
I took a gamble there, playing with my role, but thank you for accepting this. Yes.
But I have a question for you, Nikos, as well. So you were talking about doing 6-hour averages for weather prediction, and I think the weather prediction you were doing was running up to 3 days. How long can you do the not weather predictions, the water demand predictions? Sorry.
Okay, because I was about to say that the Thanasis would be more suitable to talk about the weather prediction, since he also presented us with the weather prediction module. In fact, what you saw in the HMI is the visualization of all the individual NAIADES components, not all of which we are responsible as Konnektable. However, in the water demand prediction, we do collaborate with our colleagues from JSI, and those predictions are the setup of the prediction algorithms, let's say, was based on the needs of each individual end user. So we have predictions that are for the next hours, up to what is going to happen in 15 days from now or 1 month from now, and over an extensive period of time. We have had some good results with predicting 1 year ahead, let's say. Of course, not very accurate, but it is something that could hold some value. So yes, basically what I'm trying to say is that we have divided the water demand prediction into short-term and long-term in order to be able to better facilitate the needs of each end user. So we can have predictions that are coming hourly, let's say, and concern what will happen in the immediate next time period, up to, let's say, a week ahead, from the next hours up to 1 week ahead. And then we have a longer term prediction, which is taking into consideration also historical measures more than it takes, in fact, the actual data that are live, that come at that moment from the sensors. And it can provide a prediction for what will happen in a monthly basis, let's say, or a bi-weekly basis for up to a year, I would say. But again, this is something that if an end user has another need, and we can couple this need with some necessary for us data, we could provide for a longer period of time some predictions.
Thank you. But your water prediction model, do you see that it could be used in other sectors as well, or replicated?
Given that we are doing things that have been done in a sense before in other sectors, just adjusting it to specific needs, I don't see why it could not hold as the backbone for a similar, let's say, component in a totally different sector. So yes, I think that there is a replicability in most of what is being designed for NAIADES, because again, every single component is developed based on specific needs.
Of course. Thank you, Nikos.
Thank you very much.
I have a question for Gareth as well about smart water, smart meter projects. So,
Yeah.
What was the main challenge for a smart meter rollout and afterwards analyzing everything?
Well, I think from the stakeholders involved, there were two kind of main areas. The first one, very much from our perspective, was upskilling and cross-skilling into a smart water domain. So one of the key kind of success criteria for the Fireware for Water project is to determine how Fireware as a kind of data capture, processing and delivery platform can be used in the water sector. And then, so from our perspective, we had to get good at working with that, and that was an interesting challenge. And then I think that the second real challenge we had was integration with Southwest Water. So I think Southwest Water are in a position as a water company which isn't unique to them, and I think it's very typical for kind of historic sectors where they're primarily a water company. They're a company that deliver drinking water and they collect wastewater, and they're not a technology company. You think of technology companies like kind of Facebook and Google and companies that are working kind of on the edge of machine learning and deep learning and things of that nature. And that's kind of fundamentally not what Southwest Water are at the moment. So there's a very interesting challenge for all of the stakeholders in being able to work in that kind of environment. That's why Fireware for Water has been a really useful project for everybody. I think, like I said in the presentation, it's been incredibly useful for Southwest Water because it's given them the opportunity to kind of dip their toe into smart water in a fairly controlled and safe way by using a small pilot study and being able to work with domain experts like Fireware Organization and EGM. And I think these projects are a lot like icebergs. The presentations that we do of what happened is very much the top of the iceberg, but there's a lot more that happens under the hood. And I think for Southwest Water and other water companies, it's about how they start kind of organizing their businesses around the data they have. There's an interesting presentation a while ago from the head of technology at Thames Water, and he turned around and said, look, we've installed 50% of our meters are now smart meters. We're collecting a vast amount of data about water consumption. So effectively, we can think ourselves as being a big data company that happens to deliver water. So, the challenge there for water companies and other kind of traditional non-technology companies that work with lots of customers is how do you start working with all of this data, and then how do you make some sense out of it? And I think you can see from the other presentations that were geared around machine learning and data science, is there clear opportunities to be able to gain. But it's like all technology, data science isn't a universal panacea, and it won't solve all of your problems.
Thank you. And as you're talking about the fireware project for water, so what are the main benefits of using, for example, fireware instead of your alternative solutions?
Well, this is a question we asked ourselves a few times on the project, because it's very easy to say, why don't you just use a regular database? Because effectively, what fireware is, or what the context breaker is doing, is it's providing data storage. And given that this was a fireware project, that would have been really bad form to use a database, because that's not what the goals of the project are. But I think there are a couple of things that come across the very important here. Is the first one is that for organizations that work on kind of full stack development, so things where you've got web apps or mobile apps, or just applications where you're collecting data and storing it and processing it, there is a really strong push towards using off-the-shelf components rather than building your own components from scratch. So the nice thing for us, by using fireware, it meant that the work we did with EGM, they sent one of their experts in, configured the smart meters to work with Stelios, so we could capture data. And they did that in a couple of days, and that was the beginning of the project. Now, trying to do that with writing your own database technology from scratch would take longer, unless you have to be, I think, an unbelievable rocket science in database development. Now, the nice thing from our perspective as researchers is that by not having to develop any database technology, we could spend all of our time solving hard and interesting problems, which is very much managing leak detection and working on solutions for the Southwest Water staff and the customers. And also, we didn't need to worry about the data, because the data would turn up. And, I think that's the benefit of using off-the-shelf solutions, is that they normally do stuff. And I think the most obvious thing here is we weren't going to design our own smart meters. So, why should we design our own data network when we've got a perfectly good one that already exists?
That's a really good analogy of designing your own smart meter and designing your own database, that if you have a working solution that suits all or almost all your needs, then it's better to spend all your energy and money in other research areas.
Yeah, I think it's one of the challenges of being a software engineer on a project is software engineers like solving problems. Unfortunately, a lot of the time they don't solve the right problems. They solve the problems that they find are interesting. And I think as working in kind of multi-agency projects like this, you have to be very mindful of that and make sure the problems you solve have got the right alignment to the actual problem that you're supposed to be solving.
That's a really good, cross-sectional advice for everyone, I think. But thank you, Gareth. So I have a question for Cristian as well. So when you were showing the fountain prototype where you were taking all the measurements because there isn't an off-shelf detector available for chlorides, is it a feasible solution for other end users to use as well, or is it just one-off?
Yes, it's possible. We think that these prototypes can be adapted to other similar applications. What we have to do, or what the user has to do, is to just how can I say, to take a pattern, to have a correlation from the empirical data to the measurement data, and this will probably work perfectly.
Is this affordable in a sense that how much data you get out of it and what predictions you can make on it compared to the cost of all the components and sensors that go into this?
Can you repeat, please?
Is it cost effective to use this method for prediction? So is it at all affordable way of getting this measurement?
Well, we think so. The system in the application developed under the NAIADES platform was cost effective in the sense that we use cut-off-the-shelf products, and at the same time, it's not an expensive solution. It's a very standard solution. The added value consists in the correlation work made interpolating data from the empirical surrounding.
That's good to know. Thank you, Cristian. And if no other questions come up, then I'll just ask a question or two from Thanasis as well, and that might be the wrap-up for the discussion. So coming back to weather, in your opinion, is AI reliable for weather predictions? What are your experiences?
Yes, I can say it's reliable. However, of course, it depends on how you ask it. How do you define reliability, and in what scale do you want to have predictions for? So if you want highly localized predictions, then data-driven models, yes, of course, they can provide you highly accurate predictions. But if you want to get the bigger picture, at the moment, I think it's very hard, although there are some attempts by some very high-end companies like DeepMind, which are trying to use multiple state-of-the-art methods and develop more in order to create some forecasts about larger areas, especially concerning precipitation, which is on its own a very hard problem. I mean, we look at the sky and we say, okay, maybe it will rain tomorrow. However, to define this problem and predict it is very, very difficult in terms of mathematics and all of these things. However, to the point we are now, yes, I am confident that what we are doing is accurate and it's very robust, which means that it can be implemented in similar cases, but in other location, and it will provide equally good results.
How good is the NAIADES weather forecasting toolkit with extreme weather events right now?
Right now, it doesn't predict any extreme weather events because extreme weather events are very rare. It's very hard to train an algorithm to understand something that it occurs only once every few years. However, we are working on that, and we are trying to find some solutions on how to implement this as well. However, as you can imagine, explaining to somebody who hasn't seen in his life a typhoon or a hurricane or something like this, and what are the causes that they manifest this phenomena, it's very hard to make an algorithm, train a model into understanding how this phenomena will be manifested in the future.
Okay, thank you. And do you see what other sectors could be looking into using your weather forecasting toolkit apart from water sector?
Sorry, can you repeat?
One, of course.
I lost the first part of your question.
So can this weather prediction toolkit be used in other sectors apart from water and Formula One?
Okay, yes, of course. It can be used in other parts. Actually, it can be used in any sector that needs highly localized forecasting capabilities. As I mentioned in my presentation, Formula One is only one case, and one other example is the one we are working on in CERTH. I am part of the Institute of Bioeconomy and Agri-Technology, and we are using and developing this data-driven weather forecasting toolkit to be applied in agricultural locations, in rural environments, and to be deployed in orchards in order to create specific and highly localized weather predictions for each producer on its own. So yes, it can be applied almost anywhere.
Thank you.
Thank you.
And if there are no more questions, we have come to the end of our webinar 4. I thank all the speakers, especially thank you for all invited speakers for sharing your projects and your work with us today. And thank you for everyone from NAIADES project presenting our work as well. If you want to follow us on social media, you can find us in Twitter and Facebook. And of course, you can find more information about the projects on our website. Thank you very much for joining us today. And hopefully see you in the next webinar.
Thank you very much.
Thank you, Tully, for moderating this webinar.
Yes, thank you.
You're
Bye-bye.
all very welcome. Thank you. Bye.
And thanks to Anna for the organization.
My pleasure.